Batteries are very important, and the reason why batteries are really important is because they're the driving force of technology. So before this, it was pretty much just static electricity. You're able to kind of charge up stuff like a lighting jar, but the discharge is really fast, and you really don't have this prolonged kind of way to store energy. So once the battery kind of came in with the Voltaic Pile, it pretty much changed everything. Today I'm going to focus on pretty much the lead acid battery. You're going to find tons of really good videos out there, so feel free to kind of Google them. I'm going to try to do my best to kind of summarize what I want you guys to understand. For physics, do you have to memorize these chemical reactions? And the answer is no, but to have that background just to understand, okay, there's a redox reaction happening. That's what's driving my electrons from one end to the other. That's also providing the potential difference between the two, or the voltage. So different types of materials will kind of have different voltage. And that's why we have something that's most likely about 1.5 when it comes to a typical battery, to something that's more like 5 volts or even 6 volts, which is more of your lithium ions out there. So we're going to go over it. We're going to start off kind of with the first one, which is the Voltaic Pile, and then highlight lead acid battery and kind of end there, and then I'll have you guys watch videos on lithium ions from people who do a much better job than me. So let's get started. So this is kind of the Voltaic Pile that Alessandro Voltaic made. So he actually thought the reaction that was occurring was between the two plates right here. So he actually thought it was between the copper plate and the zinc plate right here. But what he did not know was that eventually Faraday eventually found out the reaction actually occurred between here. So the reaction is happening in the sodium chloride brine. So remember, he got copper, got zinc, and then he put salt water, paper, salt, and just kept going. So this kind of created a redox reaction that he did not understand. He just knew that it happened, and he got famous because of what happened, and you were able to do things because of what he created, but in essence, he had no idea how it worked. So here's our two piles. So I'm going to kind of put my copper on this side, and I'm going to put my zinc on this side and talk about the chemical reaction that actually happens in between them. So here's my copper plates, and then here on the bottom is my zinc plates. And in between them, oops, I kind of did the opposite. Shoot, let me kind of undo that. Trash. All right, so what I have here, because I want to do it between the gaps. So here I have my copper. And then here I have my zinc. And then in between them, I have my sodium chloride solution. So I have H2O, and then I have sodium and chloride, all floating around. So it's a solution in a paper towel or some sort of paper that he soaked. Now, if you normally just hook these two up, so let's say you had a piece of copper, and then you have a piece of zinc, and you connected them somehow, let's say with a wire, electrons are going to flow in a certain direction. It's going to flow this way. And the reason is because copper is more electronegative than zinc. So together, copper is going to want that electron more than zinc does. So zinc will just give it up to copper. So even if you put like that stuff on your tongue, so if you put copper and zinc on your tongue kind of is the salt bridge. It's going to allow that electron to travel from the copper to zinc. So you kind of taste, like a reaction happening. It's a metal taste going on because it's kind of breaking down. Now, eventually this is going to stop, right? Copper is going to eventually not get enough, or it's going to get too negative, and then zinc is going to become too positive, and the reaction doesn't happen anymore. So I'm going to explain why this salt gap is very important. So here's the two half reactions. For zinc, you have zinc solid. That's eventually going to become a zinc ion and 2 electrons. So this is you're losing electrons. So the Leo Gers, losing electrons is oxidation. I was about to say reduction. So this is your oxidizing side of it. On your other side, the redox, or the Leo Ger part, gaining electrons, you have copper 2 plus 2 electrons will give you copper solid. And this is your other side of it. This is your redox or reduction side of it. Okay, so these are the two reactions happening. Electrons are going to travel this direction into the copper, which is going to drive this reaction, and this reaction is going to drive the electrons out. And like I said, eventually it just can't do that anymore because copper is going to become, technically it can't provide the 2 pluses anymore. So what's going to happen is there's going to be reaction in between the solution itself. So what happens here is actually pretty interesting. Water is going to be changed into OH minus and H2. So you're going to create hydrogen gas and hydroxide ion. And this hydroxide ion is going to help supply the Cu2 plus to kind of drive it and also help accept this reaction that's going to occur. So that's what's going to drive this side. On the other side, you're going to have, remember, you have zinc plus, so you need something to kind of cancel that out as well. So what's going to happen is on this side, this chlorine is going to donate its electrons into that. So it's going to help balance the reaction out. So you can have this one here, this one here. So the chlorine is now going to be taken up on this side of the reaction. This side's going to produce a negative. So what's going to happen is sodium is going to balance out that side. So the production of this, so if you have copper, zinc, and you have a salt in between, what's going to happen is it's going to create hydrogen gas, chlorine gas, and also sodium hydroxide. So you're going to have this acid just like bubbling out from this thing as it kind of reacts. So it's pretty cool. It's pretty crazy. Kind of dangerous. But this is the reaction of the Voltaic pile. Now, if you ever Google it, you're going to have something kind of different. So this is the chemistry that happens inside, and it wasn't really understood until Faraday. But even if you Google it, you might see something more like this one. So here is kind of the same thing, but it's going to be isolated more. So instead of having zinc and copper touching each other, you kind of have them opposite ends in two different solutions. Both are in sulfuric acid, and you get the following. Now, if you look back to my previous picture, if you have the following solution. So this is a copper, whoops. So this is copper sulfate. So in solution, you're going to get, I should have chose a better color, copper 2 plus and an SO4 2 minus. Okay, now if you dip a piece of zinc in there, what's going to happen is that they're going to trade places. So you're going to get zinc 2 plus as a solution or ion with the SO4 2 minus. And then what's going to happen is you're going to have your copper as a solid forming on the metal itself. Remember, because copper is more electronegative, it's going to take the electrons from zinc. It'll be happy to replace itself with the zinc. And then that's what you get, a precipitation reaction between the two, and kind of exchange. Now, if we separate the two, we can kind of harness what's going to happen. So just like before, you have a redox reaction. You have this side, which is zinc, which is going to give up its electron to be zinc 2 plus. You're going to have copper. It's going to accept the electron, which is copper. Now, eventually, it's going to stop. So as this reaction is going, you're going to produce more and more ions, zinc ions, into my solution. So even though it's giving up electrons from this redox reaction, eventually it's going to get very positive on the left side. The same thing's going to happen here. Remember, you're going to have positive copper 2 plus changing into copper solid from this reaction as it accepts electrons. And eventually, you're going to get very negative SO4s building up in its solution. So even though this is a reaction that does want to happen according to free Gibbs, you're going to have this driving force of electrons that's going to be pushing through. What's going to happen is that eventually this side's going to be very negative, this side's going to be very positive, and it's just going to stop. So the clever thing is, if you have a salt bridge, of both potassium and chloride, what's going to happen is going to help balance out the charges. So the chloride is going to go onto this side, while the potassium goes on this side, and it's going to push the reaction further because of the balance of charges. So that's pretty cool. And this is kind of the galvanic cell or voltaic cell that could happen based on the ideas of the voltaic pile with the similar metals, but a little bit more efficient because now you kind of have a better driving force of the reaction. Now the lead acid battery is very similar to this, but it uses materials that are very cheap and it's reversible. So I'll kind of show you. So here is a normal lead acid battery. You have plates of two different metals sandwiched very close together. You have it flooded with with acid, sulfuric acid, and then it's going to help promote the reaction of the two metals. You have lead and lead sulfite. So here is the two reactions that's going to happen. And they both form the same product, lead sulfate. So you have lead oxide, it's going to form that. So let's talk about the two half reactions that are actually happening. The oxidation side of it is going to be Pb solid, Pb2+. Okay, to facilitate that, you're going to have sulfuric acid involved. Okay, so it's going to become 2+. You have sulfuric acid is going to help balance out the charge. So first we want to balance out our elements. Do we have the same amount of elements? And the answer is yes. One lead, two sulfates right there. But the charges are wrong. This one's neutral. This one is 2-, and this one is neutral as well, so we're going to have to add some electrons right there. So this is where the oxidation is happening. Remember, Leo Gers. So losing electrons, oxidation, so this is oxidizing. So the the reduction side is PbO2 changing into Pb2+. We also have this in sulfuric acid. Plus SO4 2- is going to give me PbSO4. So same kind of half reaction here. Let's balance out the elements. One lead here, one sulfur, but we have 6 oxygens on the left, only 4 on the right, so we're going to balance out with water. Since this is in acidic solution, H2O, we need 2 of them. Now, unfortunately, when I do that, I added some hydrogen, so I'm going to have to add up 4 hydrogens on the left as well, so I'm going to add it as hydrogen ions. So let's make sure it's balanced now. 1 lead, 1 sulfur, 6 oxygens, 1, 2, 3, 4, 6 oxygens, 5, 6, 4 hydrogens. Now we need to balance out the charge. This one is 4+, 0, 2-, 0, 0. So I have an extra 2+ here, so I have to balance it out with 2 electrons here. So this is the gaining electrons reduction. So here we're gaining electrons, here we're losing reactions, and that's going to be the transfer of the 2. Now what's going to happen is, like the galvanic cell or the voltaic cell, we're going to try to isolate those 2 things so that we could kind of take advantage of it. Because if we just put it into a solution and smash them together, like they're connecting, it's just going to happen. But we want to harness the electrons flow as it goes around. So you're going to isolate it, put it in solution, so it's going to drive this reaction through the wire itself. What's cool about the lead acid battery is that as this reaction is happening, the precipitate actually just forms nicely, kind of nicely, on the cathode and anode itself. So it's reversible. So if you force electrons the other way, it's just going to reverse the reaction. The lead sulfate is going to change back to lead and lead oxide. So this is something that's been used since the 1800s. Lead acid batteries have been around and we still use them. I use it. They're in almost all cars. They're in my household. They're in my son's toys like Power Wheels. because they're relatively cheap and they hold a good amount of energy and power based on what it has. Now, it can't discharge fully very well, so you can't really do a deep cycle. Some are designed better to do deep cycles, but they're just not as good as running the car. They're good at starting the car up, but they're not good at continuous power. So that's when lithium ions really come into play. But lead acid's really cool. So kind of what you want to understand is batteries are pretty much redox reactions. One side is gaining electrons, one side is losing electrons. That push between them is going to drive our electronics. And right now we just need to find the best way to do this reaction that's environmentally friendly and also cost effective, and in the end light. So it's kind of a combination of what's the lightest that could give you the most power, that's the most cost effective, that's not a rare earth material that we need to go digging somewhere. So that's kind of the balance. Hopefully that makes sense. And that's it.